Statistics Lecture 9. Last time we talked about the standard normal distribution and how z-score transforms a regular bell-shaped curve with mean value mu and standard deviation sigma as the standard normal distribution. Now I also want to add that there's another way to think about the z-score. If you look at the formula of the z-score, here's what it's doing. You're taking the difference between the random variable's value minus the average, and then you're dividing by the standard deviation, which means you want to know how many multiples of the standard deviation that z is away from mu. And to illustrate this, let me solve a question. Let's say x follows, this wiggly line means it follows. So if x is a random variable that follows the normal distribution with mean value 30 and standard deviation 4, in other words, you're thinking of a bell-shaped curve where 30 is the mean value and 4 is somewhat related with the width of this bell-shaped curve. And just imagine that these are just a bunch of samples at different values. So if you randomly pick something, right, you get some value, right? Sometimes you might end up with selecting something larger than 30, sometimes less than 30. But now let's say that you get a random value for the random variable as 20. So 20 was randomly selected. And by the way, this bell-shaped means that there's more probability of getting a number closer to 30 than away from it, right? To get a number that's very small, much smaller than 30 or much bigger than 30 would be harder to get because you have more stuff here, okay? Alright, so with that, I want to know how far these two are. Well, of course, if you do 20 minus 30, you get negative 10, so there 20 is 10 less than 30. And then since 4 times 2 is 8 and 4 times 2.5 is 10, and 4 is the standard deviation, sigma, you can see that this difference, this distance, negative 10, is 2.5 times the sigma. So you can say that 20 is 2.5 standard deviation lower than the mean value, right? And that same calculation is captured here. You plug it into the formula for the z-score. So you do 20 minus 30, which is negative 10, and you divide by 4. Negative 10 divided by 4 gives you negative 2.5. And as we can see, that 20 is 2.5 standard deviations less than the mean. Okay, so I'll be using this fact a little later for the confidence interval. But for now, let's try to revisit the word problem for normal distribution, because I only did one example and you have to have some more experience with these. So here's a data. It says daily calorie consumption of US adults is 2,929 calories with a standard deviation of 476 calories. And the first question is, what percentage of population consume more than 3,600 calories? Well, you have to realize that this right here, oh, there's something I forgot. I should have added that this data is approximately normally distributed. Because if it's not normally distributed, then we can't use the standard normal distribution. But if it's mostly like a bell curve, then we can use the standard normal distribution. And when you have any kind of question that deals with the normal distribution, you always want to calculate the z-score first. So let's try to do the z-score. Z is equal to 3,600 minus 2,929 over 476, and it gives you 1.4 something, and if you round it, you get 1.41. Okay, then what you want to do next is to think about the bell curve and think about what this means. See, because the 1.41 is a transformation of 3600, and we're looking for something that's more than 3600. Here in the standard normal distribution, you want to look at 1.41. So let's just say this is 1.41, and we are looking for more than 1.41, so it's this part. Okay, so that's what we're trying to know. We want to know what percentage is this portion out of the entire thing, which is 1. So we just need to know the area of this part. Okay, so how do you find the area? Well, you can use either the table or you can also use the calculator. Let's just go with the table first. So what you want to do is you want to look at the normal distribution. This is the normal distribution table. And because we're looking for the value at 1.41, think about this right here. This is 1.4. And if you add 1.4 to 0.01, what do you get? You get 1.41, right? So you're looking for the place where this 1.4's row and 0.01's column meet, and they meet right here. And therefore, that's the value. But unfortunately, as this table says, the table values represent area to the left of the z-score, and therefore this value 0.92073 is not the area that we were looking for. It's instead the area on the left side. It's this side. This is 0.92073. And then if I want this part right here, then what should we do? Well, we know that the entire thing is 1, so you have to subtract from 1. So after doing 1 minus the value you got from the table, the answer will be 7.93%. Now, in addition to this, you should also know how to do the same thing with a calculator. So in order to get the same calculation with a calculator, instead of using the table, what you want to do is you want to take the TI-84, press second and then vars. It will take you to the distributions, and it's the second one from the top. That's because the first one is called normal PDF. PDF is talking about the value at each point, but when we are doing area here, area is from something to something, right? It's area over some interval, and because of that, you need to use the cumulative distribution function. Anytime you have an interval, you need the CDF. Only when you need to know the value, you use the PDF. So for this problem, if you use the PDF, you're going to end up with the wrong answer. So let me show you how that's done. Let's try second vars. That gives you distribution, and as written here, you use the second one, and then once you click it, you get these menus, and the lower end is, well, the interval starts from negative infinity, and because TI-84 doesn't have a symbol for negative infinity, this weird number negative 1E99, that's just a way to write negative infinity. It's really 10 to the 99th power with the negative sign in front, but to this calculator it's as good as negative infinity. Now it's extremely hard to put that number back if you mess this up, so I advise you not to change this. Just leave it like that, and then only put the upper number as this 1.41 that we want to find out. And then the other one, mu is 0, sigma is 1, because we're working with the z-score, and z-score follows the standard normal distribution whose average is 0 and standard deviation is 1. So you never change these these two numbers. Don't change the lower. Just put 1.41, and then if you do the paste, if you go down and click paste, you'll see that the value that you get is exactly the same as the table, except that it actually has a few more digits because the calculator can show you more. So that's what you do for finding the value of the area when using the calculator instead of the table. But after this, the idea is the same. You still have to take this number and you have to do 1 minus 0.92073 to get this answer. Another note is that depending on your operating system, if your operating system installed is old, then you don't see this menu. So unfortunately, you will have to plug in the numbers here. And because plugging in -1E99, the first spot, is very hard, just put something that's negative and big. Okay, so some negative big number, and negative 1000 is good enough. It's good as negative infinity for at least for this normal CDF. So just put -1000 and 1.41 for the next number, and mean value 0 and 1 is the standard deviation. So if you do this for an older OS, then you will get the same answer as what I see here. Okay, now let's move on. Second question, what percentage of the population consume between 2,000 calories to 2,500 calories? Again, you're doing normal distribution, so if you're given values, you have to convert them to z-scores. So here's what I did. I did 2,000 minus 2929 and divided by 476. It gives you -1.95. I just rounded to the nearest hundreds because if you're using the table, you can't use these extra numbers. Although if you're using a calculator, you may use these as well. All right, but we have these z-scores. What do we do with it? Well, look at what it says. We want the population between the two numbers. So if you put these on the number line in the normal distribution, and look, think about this part as -1.95, this one is -0.9, and we're looking at the in between. So that's why you end up with the shaded area. So here's -1.95, and this is -0.9, and you have things in between. Okay, so how do we find the area when it's between two numbers? Well, here's the idea. If I have everything up till -0.9, this much shaded, right? And then I subtract, it should be more symmetric, subtract this tiny piece, -1.95, this part. Then if I take the difference between them, see, this portion right here will look like this portion here. So if you take away this blue part, you're left with this much, which is exactly what we want, right? So we need to find out the difference between these two areas, but this area, you can look at the table to figure this out, or you can use a calculator, right? So you can, this means we're looking for the area left of -0.9, and this is the area left of area left of -1.95, so we can subtract them. So we can do this, and to do the first one, you would need, let's see, second vars, normal CDF, put in -0.9, enter, 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 and you get 0.18406, and then you have to do this again, normal CDF, and then this time you want 1.95 with the negative, paste, and you get this one, and now you have to subtract the two numbers, so you have to do 1840600, and then minus 0.02558798. And if you do that, it's 0.15847, so 0.15847. Okay, so it's more like 847. So if you round it to the nearest, it's more like 8. Okay, so that's the answer. Alright, let's move on to the third question. What is the third quartile or upper quartile, Q3? Well, so you have to know that upper quartile is something that would contain the 75% of the population if you measure from below. So the idea is like this. If this is the bell curve of the entire population, we're looking for this spot, this question mark, where this much will account for the 75%, or 0.75. That's Q3, or the upper quartile. Now, Q1 would be 25%. It's not equal, but the value at Q1 will give you the area of 0.25. Q2 is just another name for the average. And then there are a bunch of other cases that you can have, like a 70 percentile or 60 percentile. If you use percentiles, you can also talk about other places. Sometimes that's important too. But that's basically the idea. So how do we do that? Well, so let's think about the following. We're trying to figure out what the area, what number the area gives you 0.75. That's really what we want. And 0.75 comes from the fact that we were looking for the upper quartile. If this was the lower quartile or the first quartile, this should be changed to 0.25. If we were looking for the 60 percentile, then this would change to 0.60. Okay, so we're looking for a certain value where, if you look at the left of that, you get 75%. So if this is the standard normal distribution, and we're looking for, so here's 0, and we're looking for this spot right here where this would be 0.75. Now, there are two ways to get it, again, by using the table, or you can also use your calculator. Let me show you how to do the table way. So first, in here, you want the value of the area to be 0.75. So instead of going for 0.75 here, you look at these values and see which one gives you value close to 0.75. And if you look at right here, 0.75175, you see that, right? So that's very close to 75%, but this is also very close to 75%, right? So these are both close to 75%. If it's much closer to one of them, then just choose one over the other. But this is like what, 0.00140 away from 75%, and this is 0.00175 away from 75%. So, you know, the value is slightly closer to this one than the other one, but it's almost like in the middle. So I would just take the average of the two. So this is on the row of 0.6. So this one is given when you have 0.6 plus 0.07, which is 0.67. And here you have 0.68 to give you that, right? So you need to take the average of the 0.67 and 0.68, which is 0.675. Okay? You add the two numbers and divide by 2. So we know that it's really 0.675, where the left side of that would have the area of 0.75. So that much we know. We know that if you have a normal distribution, and here is 0.675, then the left of it, this much would be 75%. Okay. Now, but that is the z-score, right? And that's not what x is. X follows a bell curve or the normal distribution with mean value at 2,929 and standard deviation at 476. So you have to convert z back into the x. And this time what you have to do is, instead of using calculating the z-score, you have to set the z as 0.675 and come up with this equation. And we have to find x. And this is not that hard to solve. You just have to multiply 476 both sides. So this cancels, and you add this to the other side, right? So that will give you 0.675 times 476, and you have to add the 2,929. And if you do this with a calculator, you will get 3,250. So the third quartile will be 3,250. In other words, the 75th percentile in this population consumes 3,250 calories per day. And because if it's 75% from the bottom, this would be among the top 25%, right? 100 minus 75 is 25. So you can say that a person that is eating at top 25% is eating at 3,250 calories per day. That's another way to look at it. Okay, next question. Now, the confidence interval is something that I haven't explained. So this is today's new material. But before actually explaining what the confidence interval is and giving you the formulas, it's actually better to solve this together. So to briefly explain what confidence interval is, it's an interval that's centered around the average, the mean value, and it has to be symmetric. So it's if this distance is 5, then this should be 5 as well, and if this is 100, this should be 100. So these two distances should be the same. Okay. And what you want to do is, for confidence intervals, they should always be given the confidence level. And this level is given as 90%. That means this area right here that's captured inside the confidence interval, that has to be 0.90. That's what we want. Okay, so once you figure that out, what do? Well, you have to use the standard normal distribution. So go to the standard normal distribution and think about these two values where these should be negatives of each other, and it should capture 0.90 as the area. Now, how can we figure that out? Well, first, think about the following. If you divide the 90% by 2, you get 45%, right? 90% divided by 2 is 45%. So what I know is that this red part right here, this much right here, this much is 0.45. Okay? And then because the tables are given to you as from negative infinity to that number, you should now ask, what if I had everything from the left side until here? What would this area be? And for that area, you just have to add 0.5 to it, because this much is 0.5, isn't it? So 0.5 plus 0.45 gives you 0.95. So this point right here, I don't know what that is, but I do know that this area, if you measure from negative infinity up till that right boundary right here, should be giving you 0.95. Or, in other words, this place should be the 95th percentile. So that's what you have to find from the z-score, okay? So you want to find the right bar where including this part, the entire left side of it is 0.95. And to do that, you can again use the table to figure out when that happens. But now this time, let me show you how to use the calculator. So in the calculator, you can use the inverse norm. It's same as before. You do second vars, and you go down and you use the inverse norm. And for the inverse norm, you take the area as, what do we want? We want 95 percentile, right? Don't touch the mu and sigma, just paste that. And it gives you the z-score that's needed for the 95 percentile. And if I round it up from 8, this would be 1.645, right? So that's how I got this 1.645. But once again, this is a z-score, right? So now what you need to do is you have to solve the z-score formula for x. So again, you multiply this, add the 2029, and you have to calculate this in order to find that right bound. Furthermore, I forgot to include it in the slide, but if it's negative 1.645, because we know that if the positive side is 1.645, because of symmetry, this part would be negative 1.645, right? So if I solve the exact same thing with 1.645 replaced by negative 1.645, that's going to be exactly same as before, but with the minus 1.645 times 476. Okay, so we have these, and you should use the calculator. So let's see, 2929 plus 1.645 times 476, and then 2929 minus 1.645 times 476, and these two numbers, 214, you could round that 214, you can round to 2146 until 3712. So 2146 to 3712. And you write down your answer like this. You can use an interval notation, like the closed interval 2146 comma 3712, or you can also use this notation with a inequality. So your random variable belongs to 2146 until 3712. Okay, so that's the answer for this question. Okay, so hopefully that gave you some idea of what confidence interval is. And in general, this is what happens. So the definition of the confidence interval is that it's a symmetric interval centered at the mean value that contains some percent of the population given by the confidence level. So in the previous question, we had the confidence level 90%, right? And I just used the graph to figure out that it's equivalent to saying 95 percentile. But here's a more step-by-step method. So when you're given the confidence interval, you want to follow these steps. So step 1, you have to convert the confidence level to this alpha value, where alpha is also called significance level. So you get alpha as 0.10. And in terms of the graph, what this means is that if you have the left and right symmetric with respect to 0, and this much is 0.90, then doing 1 minus that gives you this other part. So this is the 0.90, so if you do 1 minus that, you end up with the part that's not shaded. So this part right here and that part right there. It doesn't look symmetric, but it should be symmetric if I drew better. And so I know that these red stuff added together gives you 0.10. However, you want to divide that by 2 to find just one portion of it, which is 0.05. And then once you have 0.05, you can do 1 minus 0.05 to see that indeed what we want is the 95 percentile. So that's the formula. So the step is find the significance by doing 1 minus confidence level, and then you do 1 minus alpha over 2 to find exactly what the area should be if it's on the left side, and you take the inverse norm of it. Okay, so that's how you get the right critical number z alpha over 2, and then the left one will be negative z alpha over 2 by symmetry, right? So you do that, and we got the value 1.645 using the calculator, and once you have that, then you do average minus the critical value that you found. By the way, this is called a critical value. So you use the critical value, so you subtract and then add critical value times the standard deviation. So that's what you do. Okay, I guess if we do just one more following these steps, you will probably understand better what to do. Okay, so here's what we want to do. Suppose x follows the normal distribution with mean value 40 and standard deviation 7.2. And the question is, find the confidence interval at 94% confidence level. And first, the confidence level is 0.94, and therefore you calculate alpha as 1 minus 0.94, which is equal to 0.06. And then once you have that, then you go back to the formula, which is the critical value being inverse norm of 1 minus alpha over 2. And rather than trying to memorize this, just think about the picture why this makes sense. Then it will be very easy and comfortable using this formula. It's always better to understand the formula and use it than just using the formula without any understanding. Okay? And this is not very hard to understand, so you should really try to look at the graph. Okay? So I just apply that to what we have, and you have the critical value equals to inverse norm of 1 minus 0.06 over 2. And I'll skip the calculator part, but it's exactly the same thing. You do the exact same thing, and using the calculator, you will see that the value is 1.881. And once you find this critical value, then the confidence interval is just mean value minus the critical value times the standard deviation, and mean value plus the critical value times the standard deviation, and x has to be between those two. And finally, if you use the calculator, you get these two numbers. Now I want to give you some more idea of why these numbers are reasonable. So see, x follows the bell curve where the mean value is 40, and 7.2 is the standard deviation, and we know the 68, 95, 99.7 rule, right? Which says if you go one standard deviation above and below, so adding 7.2 to 40, you get 47.2. 40 minus 7.2 would be 32.8. And for these two numbers, if you look at this shaded area, this will be 68%, because that's just one standard deviation above and below, right? Now what if you go two standard deviations, which is 7.2 times 2, which is 14.4. So if you add 40 plus 14.4, let me use a different color, that's going to be right here, which is 54.4. And then 40 minus 14.4 would be 25.6. Okay. And if you take from here to there, if you take this much, then the 68, 95, 99.7 empirical rule says that this should contain 95% of it. Okay. Now look at what we're looking for. We're looking for 94%, which is very close to 95%, right? Therefore, the numbers that you get should be very close to these numbers, and indeed you see that they're very close, right? Because 95% has to cover more, these values will be wider than what we have here. Okay, so that should give you some idea of why these numbers do make sense. And you know, having those making those judgment will actually allow you to make allow you to understand this better, and it can also help you to avoid errors, right? So that's all for today.